After we are done with covalent and metallic compounds, let's look at ionic bonds and ions. Again, this is a new chapter in your textbook, and please read it carefully. Ionic bond is one more case of chemical bond its nature is purely electrostatic. It's electrostatic force between positive and negative that holds ions together in ionic compound. Well, in general, you can say that any interaction between positively charged atoms and negatively charged atoms represents some sort of ionic bond. It's purely electrostatic again. Plus attracts minus. So if I have lithium atom, I have fluorine atom, 1 electron on lithium, 7 electrons at neutral fluorine. You may have a lithium plus and fluorine minus when 1 electron jumps from Li to F. Here we have 1s2, 2s1. Here we had 1s2, 2s2, 2p5. Now we have 1s2 configuration for Li plus, which is helium, noble gas configuration. And then we have 1s2, 2s2, 2p6, which is neon electron configuration. So both lithium and fluorine now have noble gas configurations, which is stable. You can say that lithium donates electron and fluorine accepts electron to make ions. Then ions interact to make ionic compound. So metallic, you can look at it at this cartoon representation, very big atom of lithium, much smaller atom of fluorine. You remember when you are going from first group to seventh group, size of atom will drops down. But then lithium loses 1 electron to become Li plus, much smaller. Fluorine gains 1 electron to become fluoride, F minus, much bigger. Usually cation is smaller than an ion. With ionic compounds, you seldom see molecules. Ionic crystal exists in a three-dimensional array of cations and anions called lattice structure. We were just looking at lattices of elements for metals. When we write formulas of ionic compounds, we always write an empirical formula. The smallest whole number ratio of cation to anion. Ionic radii of negative ions always larger than of elements. Of positive ions are always smaller than of atoms. Lithium is going down and dramatically smaller. Fluorine is going upwards and it's dramatically larger. Now, when you remove 1 more electron, size of ion drops down. Size of ions going up with period of periodic table, no matter is it for positive ions or is it for negative ions. In general, negative ions are much larger than positive ions. Negative ions of iodide is practically the largest. You cannot see anything resembling this for positive. The only big positive ions are rubidium and cesium, and their counterparts, thallium. There are a couple of larger ions here as well, not shown in this chart. But most of metal ions are dramatically smaller than anions. Now, how we measure size of negative ion? Where the positive ion ends and negative starts. A very common agreement is to fix size of oxide ion, which is very common, at 1.40 angstrom or 150 picometers, and then use this for calculation of all other ionic species. There are different types of atomic radii, and you should be very careful when you are taking atomic radii from different reference book or different sources. They may disagree. Now, how positive and negative ions are arranged? Again, we have close packing principle. So smaller positive ions should fit between larger negative ions which repel each other. So if you have very small positive ion relative to negative with ratio positive to negative from 0.16 to 0.22, coordination number will be 3 and it will be sitting inside triangle. If you have size from 0.22 to 0.4, you'll have very common tetrahedral arrangement. This is relatively common case. From 0.4 to 0.73, you'll have again another common octahedral arrangement. Beyond that point, you have cubic. Only if radii of positive and negative ions are identical, you can have close packing with coordination number of 12, like we have seen in most of elements. That can happen only for compounds of cesium and rubidium, and there are several other exceptions. So let's look at what happens in nature. There are not too many types of structures that are very common. On the other hand, there are literally thousands and tens of thousands of different crystal structures, but most of them adhere to several simple groups. First, cesium chloride for very large cations. It's cesium chloride itself, thallium iodide, and several alloys like cesium gold, copper, zinc, so on. Another group is fluoride, calcium fluoride, uranium oxide, and so on. Rock salt sodium chloride give it name to large class of compounds that have very similar structure, one-to-one. Another one-to-one common structure is zinc blend, cubic structure that gives plenty of one-to-one structures like cadmium sulfide, gallium arsenide, gallium phosphide, indium arsenide, zinc oxide, so on. Wurtzit, another polymorph for zinc sulfide, is hexagonal. Again, there are plenty of binary compounds of that sort. There is a large group named spinels, and we'll look at them as well. So, all these names, by the way, are coming from mineralogy. Geologists and mineralogists are studying crystals for a long time. These crystals are beautiful, so it's very interesting study. And the names are coming from them. They are using plenty of fancy names. So let's start with sodium chloride. Everybody knows sodium chloride. Uh, the structure of sodium chloride is cubic. So you have larger chlorine atoms, here they are green, and smaller sodium atoms. This is how unit cell looks like, and each side is equal to 2 radii of sodium, so diameter, and 2 radii of chlorine. So when you know the side of this cell, you know total of sodium and chloride. If you know one of them, you can calculate another radius. Coordination number is 6. We can look at it here. You can see that each sodium is surrounded in octahedral fashion by 6 chlorine atoms, and each chlorine atom is surrounded in the same exactly identical octahedral fashion by 6 sodium ions. Now, cesium is larger than sodium, so it packs with coordination number 8. It can be drawn like cesium sitting in the center, having 8 chlorides around them at each vertex of the cube. The same structure can be represented as 2 cubes glued inside each other. So you have 8 neighbors around each of them. You still can calculate side of this cube knowing radius of cesium and radius of chlorine. It will be one side multiplied by square root of 3, looking at diagonals. So one atom inside, 1/2, 1/2. So 1/2, 1 radius, 2 radii, 1 more radius. It's interesting that molecular ion NH4 can crystallizes in the same position.